Welcome to the second interaction session for control systems. My name is Soumya and I am a PhD student at IIT Gandhinagar. So today we have some sample problems that we'll be solving to clear your concepts on week 2 session that was taught. So let's start with some questions. But before that, in the last interaction session, what we had really done was we tried to understand the basic maths. How do you find the roots of quadratic equation? In some cases, we learned that what would happen if we take the time response of a system. In other cases, what would happen if the same question is solved using Laplace transform? So, I hope the things were clear. This session, you might have already studied the transfer function and BIBO stability that was covered in the NPTEL session, the normal lectures. So we'll have some questions related to them. Before that, I hope with the practice in the last session, you are already familiar with the Laplace transforms. So the most general Laplace transforms are here, and I think even for the questions later on, we'll need all of them. Not all of them, some of them. Please take a screenshot or a snap of this Laplace transform. We'll be using them throughout the session to solve the questions. So the important ones are this unit step response. 1 upon s is the Laplace transform for this. E to the power at is the one. Sine at, cos at, all of them will be using them back all the time. So please, and for your information, all of these are very important. Uh, Differential one is also important, and you're going to use them everywhere. It is going to be the foundation for the control system course. So once you derive them, try to have them in mind. And when you practice questions too many times, then you're already going to have them. Mostly you'll be able to use them very efficiently. So, okay. Then we'll start with some questions. So, the first question is, the response of a system to an external input is called. So I think you've seen the lecture, and then you've got something called forced response, free response, some sort of transient response, some sort of steady state response. So can someone tell me what is the answer to this question? If it
Forced
is
response, madam.
yes, forced response. So why it is forced response actually? So in the lecture also this thing was covered, and I want to reiterate the example. So it is forced response because let's say we consider a mass spring damper system. Okay. So we have some input to the system. Let's say it's some sort of force. So it is Ft. We want to have some output from the system. Let's say we want to measure xt, or what is the displacement of the mass that's attached to a spring. So if it is a mass spring damper system, then you might know that the equation, it is uh, represented by the following differential equation, is equal to Ft. So this is the differential equation. So it is in time domain. Now what we want to do is just to have everything not in the form of differential equation, rather in the form of some Laplace transform to make the solutions algebraic. We would take them to frequency domain, and we'll use some frequency domain analysis techniques. So this is one way of understanding transfer functions. I'll show you. So what you will do here? What is the Laplace transform of x double dot t? Can someone tell me if you refer to the table that I showed?
S square into x of s, madam, when initial condition is 0.
Yeah, we will start with the initial conditions and we will arrive at something. So we'll also take the Laplace transform so that initial conditions are taken into account. S square S initial condition of 0 minus x dot 0. Okay, plus C into S of xs minus x0 plus k into xs is equal to fs. Now after this, we will try to separate out the xs term. So it would be ms square plus cs plus k into x of s is equal to ms plus c into x of 0 plus mx dot 0 from here and then plus fs. So what we try to do is we want to find out what is the relation between output and input. So output here is xs because xt was the displacement that we wanted to find out as our output and input is our fs. So we want to have some sort of relation between output and input. Now they are governed by two things. One is the initial condition and one is using some external input. So let's say we want to separate out both the terms. So what we do is we want to take this term and in the denominator we'll have ms square plus cs plus k plus the other term which includes the input. So it would be ms square plus cs plus k into fs. So when you write in this way, there are two terms basically. This first term that you have got from the initial condition, this second term which you have got from the input, some forced input. So because this is from the initial condition and it is due to natural non-zero initial condition of the system, it is known as free response. Because this is from an external input, this is known as forced response. That is why when we had the question here, the response of the system due to an external input. So the external input in our example is the force that is being applied. So the external input would be giving you a forced response for the system. Okay. I hope it is clear and it was in the lecture as well. When you know about all of these, that what is forced response, what is free response, then let's say I consider that all the initial conditions are zero. So what I say that initial conditions are zero. What that means is x0 is equal to 0, x dot 0 is equal to 0. The initial,
Madam,
yeah,
it is free response go up, madam.
yeah.
Here, 1 by FFS will come, madam, in initial conditions. There, FFS will not come, madam.
No, I wanted to separate out the terms.
Here, initial conditions, FFS will come in denominator, madam.
Okay, wait just a second.
In initial conditions, madam.
Yes. Just a second. SS of 1 S. Hmm. So when I take this, yes, it would
And
be
in transfer function, f of s will not be there, madam.
wait. On
F
FS.
of s will cancel.
Yes, so I did not have to have FS here because the output is only x of s and it is not f of s. So I was going to make you understand transfer function. So yeah. So now it is fine.
Yes, madam.
Yeah. So I wanted to show what is the output of the system, and it is just x of s. So x of s is driven by a free response and a forced response. So obviously fs has gone to the right side. So XS is the output of the system. Now, when initial conditions are 0, XS would just be 1 upon ms square plus cs plus k into fs. So, XS upon fs would be 1 upon ms square plus cs plus k. This is the transfer function for this spring mass damper system. Now, what is transfer function? How do we define transfer function? It is basically the ratio of the, let's say, Laplace transform of input to of output to Laplace transform of input given initial conditions are 0. So this is the transfer function of a system. You just take everything into Laplace domain. Once you have everything in Laplace domain, make the initial conditions to be 0. So this is yeah, and you have understood forced and free response. Okay. So we'll move to the second question. A second order system is governed by, this is a second order differential equation. So its transfer function is. Now can all of you derive the transfer function of the system? You just have to convert them into Laplace domain, make the initial conditions 0 and find the ratio of output to input. Please let me know the answer. Or none of you say the answer right now. Whoever has done, just raise the hand. Please, this is very important. This would be taking you to all other questions as well. And it is a very simple concept for the whole course. Okay, Ankit has done. Who else?
Ma'am, it's option C, 1 upon s square minus 2s.
Yes, it is correct. Has everyone got the answer? So how do you do is, I'll explain you for this question, and from the next question, please try on your own. So from the Laplace table that I've already given you, you would find that for second order differential equation, what you get is s square ys, and then you will have some initial condition term, but we are going to have anyway all of them as zero only, so we don't need to worry. The second term would be 2s of ys. So as I told, if it is second order, s square comes out. If it is first order, just s comes out is equal to us. So ys upon us is 1 upon s square minus 2s. This is a simple answer to this question, the transfer function. Okay, since you have studied this, can someone tell me where are the roots of this transfer function?
0 comma 2 madam.
Yes, 0 comma 2 is the answer. So in language of control system, this thing, the denominator, is called the characteristic equation. Okay, and the roots roots of characteristic equation are called poles of the system. Roots of uh, the numerator of transfer function are called zeros of the system. So when you start going into week 3 course, you will have both of them, poles and zeros, and these are frequently used throughout the course. So we'll be using them later on. Okay. Now what we are going to do? Okay. The transfer function of a causal system or plant is, so this was also covered in the course. Can someone tell me what are proper and improper equations, sorry, or transfer functions? Like what they have in the numerator and denominator, and how do we define them?
Proper madam.
Yeah, what happens? This is proper, right? Answer is proper. How do we define
Yes,
proper?
ma'am, proper.
Yes. So proper transfer function and improper transfer functions are defined here. So basically, if the degree of numerator is less than the degree of denominator, so it is called proper transfer function. So if I explain with an example for proper transfer function, so uh, let's say 1 upon s square plus 2. Can someone tell me this is proper or improper transfer function with reason?
Ma'am, it's proper transfer function. As the denominator is degree, it's of order 2 and the numerator has order 1.
Right, right, right. So if in the other case we had s cube plus s square plus s1 plus upon s square plus 2, it would be improper. So, okay. Now, why this transfer function of a causal system is proper, improper, or linear or non-unique? So, uh, for this course, we'll be dealing with LTI systems. But in other cases, if the system is non-linear, then also if the transfer function is proper, it is going to be a causal system. Improper is already a wrong answer, and transfer function is non-unique is the wrong statement. Transfer function is unique because you are going to define a system by the transfer function. So a unique differential equation would be used to describe the system. So it is unique. Now, uh, yeah, a causal system must be physically realizable, means it must produce bounded outputs for bounded inputs. So what happens with improper transfer functions actually? So when you're going for high response, so high frequencies, what does high frequency mean? Let's say you have this s square plus 2 and in the, or let's take this function only. Fs is equal to something of third power in the numerator and second power in the denominator. Now when you want to get higher frequency, what you will see is that this transfer function becomes infinity. So even for a bounded input, that means you have something finite, you get some infinite response. That is only possible when you have some non-causal behavior, and it suggests that the system could respond to future inputs. So that is why causal system should have proper transfer functions. Okay. Okay, so I think okay, it has been covered the poles of the transfer function. So can someone tell me what you would get ys upon us? we want to get the transfer function. Once we have the transfer function, we would have some characteristic equation. Once you have some characteristic equation, if you go to find the roots of the characteristic equation, you will definitely get the poles of the system.
S square plus
S square plus
2s plus
2s plus
2
2
divided by
hmm,
s square minus 3s minus 4
s square minus 3s.
minus 3s minus 4, and
Okay.
roots are 4 comma minus 1, madam.
Okay. Has everyone got this ys upon us the same answer, or is there
Yes, ma'am.
something different? Okay.
It's same.
Yes, ma'am. Same answer.
Okay. So it was just that you had to do s square ys minus 3s minus 4 and when you did on the right hand side it would be s square us plus 2s plus 2us. Just you have to rearrange the term, you get this thing. The characteristic equation is in the denominator. Now you're supposed to find the roots, and the roots would be 4 and minus 1. So these are the poles of the transfer function. Very good. Now, okay. So, can you tell me what are the zeros of this transfer function? Zeros are the roots that are corresponding to the numerator of the transfer function. So from the denominator, when you make it to 0, you get the poles. If you do something with the numerator, you would get the zeros. So please tell me what are the zeros?
Madam,
Yes.
option C, madam.
Okay. Minus 1 plus minus j. So what we do here is, this is the differential equation. Now again you are going to write s square ys minus 3s minus 4ys is equal to s square us plus 2sus plus 2us. So when you write ys upon us, what you get is s square plus 2s plus 2 upon s square minus 3s minus 4. Just take this term, make it equal to 0 and find out what are the roots. Whatever roots you get from here would be zeros of the transfer function. So in this case, when you would find out, you'll get zeros to be minus 1 plus minus j.
Madam,
Yes?
madam, in assignments, negative marking will be there, madam.
Is it written there in the instruction?
I don't know, madam.
I don't think negative marks are there. If it is not in the instruction, it would not be there.
Yes, ma'am, there is no instruction like that, madam. We can choose in what in exam, madam.
In exam
What
also,
about
it should not be there, but I'm not sure. You can check from the announcement section or the details about the exam. If they have written that there is negative mark, then only it will be there. Else it would not be there.
that means you are not sure, madam.
No, no, no. I'm not sure. You'll have to check the whatever is the website given to you for the course, and if they have any such declarations, then only there will be negative marking. Else it would not be there. If nothing is written, then there is no negative marking.
Okay, madam.
Okay. So we'll start with the next question. So okay, we want unit step response. So what do we understand by unit step? Unit step means at t is equal to 0, you get 1, and then it remains 1 for the whole time. Before that, you have 0. At t is equal to 0, you get a spike of magnitude 1, and it remains after t greater than 0 also. So what we're going to do is, what is the steady state value? So first thing is calculate the expression for unit step response, whose governing equation is this. Now what we were doing earlier is, we were getting, let's say, ys upon us to be some sort of numerator upon denominator, in the form which is a combination of s, or algebraic equation in S. Now, what we want is, we want this US to be a unit step. So, if this is a unit step, so in time domain, it is going to be 1 for t greater than equal to 0. What would happen if I ask you the Laplace domain? Can someone refer to the table and tell me the Laplace of unit step function?
1 upon s.
Right, 1 upon s. So what we are going to do is, this us would now be 1 upon s, and it would go on the right hand side, multiply with this term, so that you get ys. So this is what we are going to do now. So what is the differential equation? I want all of you to solve with me. Y double dot t plus 6y dot t plus 5yt is equal to ut. Now, taking the Laplace transform, what we get is s square ys. Uh, One more thing, we should have taken the initial conditions into account, but we are not taking, because nowhere any initial condition is mentioned. If it is not mentioned, we'll take the initial conditions to be 0, and take the and then use the Laplace transform in that way. 6 sys plus 5ys is equal to us. So when you try to find out ys upon us, what you get is 1 upon s square plus 6s plus 5. So ys is, us is here is 1 upon s. So here it would be s square plus 6s plus 5. Now ys can be written as 1 upon s into uh,
S plus 1 under
yeah,
bracket s.
yes. So since it is in this form, we want to find out what is the steady state value. Now from here, there are two approaches. We can take any of them. Okay. I think I have, yeah, from here I will show you the second approach. We'll take the first approach now. One of them is, you can go to S domain to time domain, and then tell what is the steady state value by placing t is equal to infinity. The other approach is, you try to do limit s tends to 0 s of fs. I'll tell this to you later, but first we'll go with this approach. So what we'll do is, you've got ys is equal to this quantity. Now I cannot have a expression in time domain, which would be very simple for this whole cubic equation. So what we can do is, we can have ys is equal to, let's say I have some a upon s plus some b upon s plus 5 plus some c upon s plus 1. If I am able to find a, b and c, so this method is called partial fraction. So when you want to break the higher dimension transfer function to some lower dimension, or not lower dimension, you want to segregate the terms, actually you would use this partial fraction method. So from here, so what is ys here? 1 upon s into s plus 5 into s plus 1, and here you have is a plus a upon s, b upon s plus 5 plus c upon s plus 1. Please find out the value of a, b and c.
A is 1 by
Wait,
5,
wait, 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 wait,
madam.
wait. I'll ask this time someone else. Let someone else also give the answer now. Hello, Priyanka. Do you want to answer?
Ma'am, value A equal to 1 by 5 and B equal to 1 by 6 and C equal to ma'am 1 by 20.
Is this the answer that you say? Please take care of the signs as well. This 1 by 6 is misleading. So check this term. And here also you have a sign issue. And this is correct.
Ma'am, here B is equal to 1 by 20 and C is equal to minus 1 by 4.
C is equal to minus 1 by 4. Yeah. Check your calculation once. There is some issue with the calculation. Do it once again. So
Yes,
B
ma'am,
is,
minus 1 by 4.
yes, and C is,
Ma'am, B is 1 by 20 and C is minus 1 by 4.
okay.
Yes, ma'am, that's it.
Yes, this is correct. So this is the answer for A, B, and C. Once you have this answer, so you can write ys is equal to 1 by 5 into 1 by s plus 1 by 20 into 1 upon s plus 5 minus 1 by 4 into, just a second, 1 by 4 into 1 by s plus 1. So taking the Laplace inverse of this. So you are already aware about the Laplace transform. If it is in time domain, you are changing it to S domain. Now what we want is from S domain, we want to go back into time domain. That is called inverse Laplace. So if you remember, for what response you had got Laplace transform to be 1 by S?
UT, ma'am.
UT. So here it is a unit step. Okay. For what time domain function in the table you would get 1 upon s plus 5?
E to the power minus 5t.
Very good. And similarly here would be e to the power minus t. So this is the time response you have got. Now what I want to find is steady state value. So if I want to find out the steady state value, that means I want to say what would happen at t is equal to infinity. So if I put the same in the equation, 1 by 5 would be there plus 1 by 20 into e to the power minus 5 into infinity minus 1 by 4 into infinity. Now 1 by 5. What would this value be? The second value? 1 by 20 into e to the power minus 5 into infinity?
0, ma'am.
Right. It would be 0. It is 0 because if you have e to the power some very high negative quantity, definitely this term is going to diminish. And similarly here. So you'll just have 1 by 5. So your steady state is 1 by 5. And this is your answer. Now, this is the first approach that you have taken. Another thing we can do is we're not going to time domain. We will just use the Laplace domain only and change the approach. So, in the lecture, it was told that there are two theorems, initial value theorem and final value theorem. Please note, initial value theorem is t tends to infinity. This initial condition. When t tends to 0. For Laplace domain, it becomes s tends to infinity and the limit is s of fs. Okay. For final value theorem, your t tends to infinity whereas s tends to 0, sfs. So what we want? Steady state value. So we'll use final value theorem. So we had a value of fs with us. Where is fs? This was fs. So I'll take this. Okay. So this was my transfer function. Now what I want to do is limit s tends to 0 s of ys. So what it becomes is limit s tends to 0 s into 1 upon s into s plus 5 into s plus 1. S just gets cancelled and what you get is 1 upon 5. So this is also the way where you can find what happens when t tends to infinity. This is also the way to find out steady state value. So please remember these theorems. These both are very important. Now, you already know the coefficient of e to the power minus t term. So it was minus 0.25. You had got minus 1 by 4. Then the coefficient of e to the power minus 5 term. You had got 1 by 20. It was 0.05. Now we'll move on to the yes. Now we'll move on to the next question. Okay. So this is the equation. And again, we want to find out the steady state value of the output. So and we have the same unit step response. Please solve this question. This is a very similar question as that of the last one. So what we want to do is we want to find out ys upon us is equal to, let's say, some transfer function. Then what we want is we want to have yt which would have this us as 1 by s, and then we want to have some expression to find out steady state value. So please proceed.
It's infinity, madam.
Okay. Okay, so can someone tell me what is ys upon us?
One upon s square plus 5s.
Okay. Okay. Then ys is definitely 1 upon s into s square plus 5s. This is basically 1 upon s square into s plus 5. When you have this, you might have found out what is A, what is B, and what is C. when you found out, what did you get, Whitey? After taking the Laplace inverse, what was the time response? Oh, no one used this method. Everyone used steady state method of Laplace transform, final limit theorem. Did someone use this method? Okay. So in case you haven't used, what you would get here is, so this would be the answer. And as t would tend to infinity, this would also tend to infinity. So if you haven't done using time domain analysis, you can try this. This is again from the Laplace table only. You have to become sure that this is the term that you are getting. So please solve using this method only. When you use the final limit theorem, what you get is limit s tends to 0 s of pi s. So what you have is limit s tends to 0 s into 1 by s square into s plus 5. You cancel out 1s and then you get 1 upon 0, which is infinity. So this was relatively easier approach when you want to have final limit theorem as compared to this method where you have to take some transforms and all. If it is sine omega cos omega, you have to again find out what to use. So all of these things come into account. So this final limit theorem is always helpful. Okay. So what is the coefficient? So yeah, it would be 0.04. You get this only if you solve using time domain analysis. And for okay. So now we'll start with something different. So you had basically two modules where you had transfer function and then you also had BIBO stability. For bounded input, what is the output? Is it bounded? Is it unbounded? How do you define BIBO stability? All sort of things are there. So
Sin
can
2t, madam. Sin 2t, madam.
okay. So can someone explain me what is BIBO stability? What does BIBO stability say? What is the full form of BIBO stability? What is BIBO there?
Bounded input and bounded output.
Yes, bounded input, bounded output. So, does this name say something? I want to share
For a
the
bounded input, we get a bounded output.
for a bounded input. So, I'll show you. Just a second. I want to change the screen, but it would not record here. Okay, so So if you see your lecture notes, I would not be able to show the screen. Maybe I can show at the end. So for BIBO stability, what was said is that if we were talking about stability and performance, and then we said that uh, if any input is such that, or let's say in other words, we can say that for all bounded inputs, we get bounded outputs, then the system is BIBO stable. if for one बाउंडेड इनपुट ऑल्सो अगर एक बाउंडेड इनपुट है जिसके लिए आउटपुट हमारा अनबाउंडेड आ रहा है तो सिस्टम इज नॉट बीबो स्टेबल दैट मीन्स हर बाउंडेड इनपुट जो हम ट्राई कर सकते हैं बाउंडेड इनपुट का मीनिंग इट शुड बी फाइनाइट एट ऑल टाइम यूनिट स्टेप इज बाउंडेड क्यों बिकॉज इट इज t axis is here t equal to 0 and this is the OT. It is always 1 throughout the time. Sign is bounded because this is always oscillating but it is in between 1 and -1. So this is always bounded. So for all bounded inputs you should have bounded outputs. That is BIBO stability. Now, in this case, what we want to check is if this is the system, what is the input for which the system output would be unbounded? So, if we do take the Laplace transform, s square by s plus 4 by s is equal to us. So, what you would get? Ys upon us to be 1 upon s square plus 4. So when you get this term, and let's say I want to check for input of 1. So can someone tell me what yt is going to be if us is going to be unit step response, unit step function? So definitely this us would be 1 by s then. Can someone tell me what would be yt? I want you to solve this. There is a shortcut way of telling this answer of sine 2t because you know what are the poles of the system. But I want to come at it after you solve it on your own. So please tell me what is yt here. Okay. Uh, if it is difficult for you, can you tell me ये किस क्वांटिटी का ये किस फंक्शन का लैप्लास ट्रांसफॉर्म हो सकता है? Can someone tell? Refer to the table that I had showed you for Laplace transform. Do you get any term where it is s square plus something in the denominator, s square some constant, s square plus some constant? Do you get any place?
Ma'am, it's been sine or cos.
It's in sine or cos. Very good. So for sine what is there? Omega upon s square plus omega square. Matlab omega is let's say the constant. So this was the thing. Now what we can do here is we can have 2 and then we say s square plus 4. 1 by 2 को बाहर multiply कर देते हैं. Now this is the thing that we are getting. So this is again bias only. Okay, that was for sine. Now what we'll do is ys into is equal to 1 by s into 1 s square plus 4. So if you try to find out, it would be ys is equal to a upon some s b upon s square plus 4. इसका conjugate के form में हम लेते हैं s plus
bs plus
minus
c madam.
yeah it would
bs
be
plus
bs
c
plus
madam.
c and then you would get what are the what is the value of a b and c. So when you try to find out some value of A, some value of B, and some value of C, what you would ultimately see is, has someone found out? Is it done with someone? If not,
A
it
is equal
would.
to 1 by 4, madam.
Okay.
B is equal to minus 1 by 4.
Okay.
C is equal to 0, madam.
C0. Okay. So what happens here is 1 by 4 into 1 by s minus 1 by 4 into s upon s square plus 4. Now ys is 1 upon 4. Okay. So when we try to find out this yt, what happens? 1 by 4 into 1 by s का 1 रह गया minus 1 by 4 into cos of 2t. So you get this sort of thing. Now you want to have steady state value. Okay, this is what the question was asking. No, the input for which the system would be unbounded. Is the system unbounded now at any time, or it is bounded? How do you decide if it is bounded or unbounded? This is the output of the system when you have decided that okay, I would give units step to the system. Is this response bounded or unbounded?
Ma'am, when will be the value are find finite, then that condition are bounded, and when will be the value are put on that condition unbounded?
Yes.
Ma'am, when will
So
be found infinite value?
yes. So in this condition, would it be infinite at any point of time? Is it possible? कभी भी कितना भी हम t बढ़ा देंगे कुछ भी कर देंगे क्या ये इनफाइनाइट हो पाएगा तो
No, ma'am.
हाँ right
No, ma'am.
the first term is already a constant second term is cos 2t it is somewhere in between minus 1 and plus 1 always so this term is always finite so this is always bounded so this says that no this is not the answer okay similarly you can check for sin 2t. So this question will solve for all the inputs and from the next question I'll tell you how to look at it. So let's say we want to check for sin 2t. So what was your ys upon us? It was 1 upon s square plus 4. Now when you say ys and us is now sin 2t. Sin 2t means 2 upon s square plus 4. So what happens is ys is 2 upon s square plus 4 ka square. You want to take inverse Laplace of this. Okay. Can someone take the inverse Laplace of this quantity? It would be in terms of sine and cos both. So if you try to find out, you can check this. It would be sine 2t minus 2t cos t. Cos 2t, sorry. So this is the answer that you're going to get. Now, if t tends to infinity, yt would also tend to infinity because you have a t term explicitly here. So this will take you to infinity and you will have unbounded. So definitely the answer to this is this option. You can check the other two options also, but you have got the answer in the second option. For the third option, it is the same way. For the fourth option, it is same way. Now, what you can really understand from here is, now you solved this much. In the first thing for unit step, what you did is you used the whole idea of us is equal to 1 upon s, and then you try to substitute, you try to find out what is yt. In the second question, in the second thing, what you did, you took the Laplace of sine 2t, and then you tried to find out the things, and you went to the time domain. But is there some other way in which we can find out? So here comes the concept of poles and zeros, and this is really important. So what was the transfer function that we had obtained? So this thing is very important. So so this is another approach. How, without finding the time response, we can say if the system is BIBO stable or not. So what you write is ys is equal to, I think it was 1 upon s square plus 4, yes. S square plus 4. Um, yes. Okay. So when I say 1 upon s square plus 4, can you tell me what are the poles of the system? What are the poles of the system? How did we define the poles of the system?
Plus or minus 2j, madam.
Yes, poles are plus or minus 2j. It is just finding out the root of the characteristic equation. This is your characteristic equation. Just find out the root. Once you have found out the root of the system of this, now what you're going to do is this frequency is already present in the system. This is plus minus 2j, and this frequency is already present in the system. This is the pole of the system. Okay. So what we say is, so how do we define BIBO stability? So there were some points that were covered in your lecture. So it was said that for BIBO stability, all poles of the system should lie in the left half of the S plane. That means you should have all the poles here or here, anywhere, but in the left half only, not in the right half. Okay? If this is the case, then this is BIBO stable. This you know already. The second point was, let's say अभी left half के अलावा और भी conditions है. So if there exists even one pole of the Planck transfer function, one pole also in the right half, then the system is not BIBO stable. मतलब if I have this condition, एक पोल तो दो पोल्स यहाँ पे है और एक पोल इधर है. This is not BIBO stable. This is BIBO stable. Okay. अभी third point is, okay, if there are repeating poles on the imaginary axis, repeating poles means, let's say two poles are at s is equal to 0, यानी पर दो पोल है. So this is not BIBO stable. So there should not be repeating pole on the imaginary axis. If there are non-repeating poles, एक पोल यहाँ है, एक पोल यहाँ है, poles occur in conjugate pair. If they are like this, or rest of the poles are here somewhere here. Okay, so this is, we say it to be critically stable, and I'll tell you why. So this is the way the things are defined. So for BIBO stability, what we want is everything has to be in the left half of the S plane. For not becoming BIBO stable, means I want to say that it is BIBO unstable. Any one pole has to be in the right half. If not everything in the left is in the left half, it is going to be unstable. If repeating poles are present on the imaginary axis, then it is not BIBO stable. But if non-repeating poles are present on the imaginary axis and only the are in the left half of the spline, it is critically stable. So this is the thing. So now this would take some time to digest, but I'll show you. See, here your bias upon US was this thing. Okay. 1 upon s square plus 4. Okay. This was already the root of your equation. Now what you did, when you said 1 upon s into 1 upon s square plus 4, you are basically introducing a pole at s is equal to 0. When you are introducing a pole at s is equal to 0, means what you are doing, there were already two poles, plus minus 2j. Okay, no real part. So one pole was here, one pole was here. You said I want to give a unit step 1 by s. So you introduced one more pole and it is here. All the poles are on the imaginary axis. Now you cannot say the system is BIBO stable. So this was one of the shortcuts of finding out that it is not BIBO stable here. You did not do all the analysis, you just have to know where are the poles located. If you understand that how poles placement would impact the stability of the system, you are going to be alright. So here, when you said I want to give unit step response, you find out इसका s is equal to 0 plus minus 2j. You found out everything is on the imaginary axis and it is not going to be BIBO stable. So for this bounded input of unit response, we are not getting bounded output, which you already saw here that yeah, we are not getting. In the second case, when you had US to be 1 upon s square plus 4. Sorry, 2 upon s square plus 4. When you said that I want to give sine 2t, तो इसमें क्या किया? Yeah, just a second. Yeah, when I showed you this, all should lie in the left half of the S plane. Yes. So if there are non-repeating poles of the planned transfer function on the j omega axis with all poles in the left half, then the system is, it is not BIBO unstable. Okay? So it is not going to be BIBO unstable, it is BIBO stable. Now when you give US is equal to 2 upon s square plus 4, that means ys would be 1 upon s square plus 4 into 2 upon s square plus 4. When you have this, what happens? You already had a pole here and here. Plus 2j minus 2j. अभी यहाँ से एक और फिर से पोल कंट्रीब्यूट हो रहा है. Plus 2j minus 2j means you have 4 poles. Now when you have 4 poles and they are repeating poles. So what was said here? If there are repeating poles of the planned transfer function on the imaginary axis with all the remaining poles in the LHP, then the system is not BIBO stable. So what you saw here is it is not BIBO stable. तो इसीलिए if it is not BIBO stable means for bounded input you did not get bounded output. So here you had yt is equal to infinity. So you can just think ki what is the transfer function of the system. Then you are going to add something. When you add something, when you are going to multiply it with something, और फिर उसके बाद poles का location देखो. If it is not in the correct place, then it is not definitely stable. So this is the way we do. So one more thing that was covered in the slide was this. See, here the poles are at plus minus j. Plus minus j पे already pole है. Means it is plus j, it is minus j. Now, when you give a unit step response, so you will have one more pole at s is equal to 0, one more pole you have got here. So, one more pole you have got here, but none of them lie in the right half of the plane. So, none of them lie in the right half of this S plane, hence, it means that it is going to be unstable. So, this is the thing, okay, which was said in the fourth point here, that if there are non-repeating poles on the j omega axis with all the remaining poles in the LHP, then the system is unstable. So this was the case here. Second part you see, cos t is here. Cos t is the input. If cos t is the input, that means frequency of plus minus j can affect. Now, अभी plus minus j है, तुम cos t दे रहे हो. That means it is also going to have plus minus j वाला frequency. Omega is equal to 1. Now this is the frequency and plus minus j is already there. You're going to have repeating poles. Repeating poles हुआ तो from the point number 4 it can be seen that if there are repeating poles then it is going to be unbounded. So it grows unboundedly. Similarly in this case 0 and minus 1 was there. अभी उसको unit step दे रहा है. That means 1 upon s. So s is equal to 0 दे रहा है. So s is equal to 0 was already there. Now you are multiplying it by 1 by s and giving s is equal to 0 once again. Okay, मतलब what is the transfer function corresponding to this? It was already s plus 0 and s plus 1. अभी क्या किया तुमने? This was ys upon us. Now what you did is ys is equal to 1 upon s square into s plus 1 you gave. So इसका s is equal to 0, 0, minus 1. You have repeating poles here. If you have got repeating poles, then it is again a problem and it is going to be unbounded. Whereas अगर cos t दिया तो this would contribute just plus minus j. अगर plus minus j आ रहा है, 0 है, minus 1 है, plus minus j है, तो वो bounded रह जाएगा. It would not be unbounded. So this was important. Okay. Okay. Please answer this question. Solve this question for ys upon us and इसका poles देखो कि ये poles क्या आ रहे हैं. ये poles क्या आ रहे हैं और उनको इनमें से कौन सा function disturb कर सकता है. Then you will just get the answer in very less time. What do you get when you try to find out ys upon us? Can
1
someone
by
tell?
s square plus 3s, madam.
Okay, 1 by s square plus 3. This
Answer is 1, madam.
just a second. Ys upon us is 1 upon s square plus 3s or self 3.
3s,
Yes.
madam.
Okay. So this is your transfer function. Now can someone tell me what are the poles of the system?
0 and minus 3.
0 and minus 3. What would disturb this system if I get one more pole at 0 or if I get one more pole at minus 3? My system would become unstable. So मुझे ऐसा ऑप्शन ढूंढना है जिसमें पोल मेरा 0 आ रहा हो, मतलब यू अभी यूएस कुछ ऐसा सेलेक्ट होने वाला है जो सीधा आके इधर मल्टीप्लाई हो जाएगा. तो ys is equal to 1 upon s square plus 3s into us. Something is going to happen, us इधर आके मल्टीप्लाई होने वाला है. Now we can say कि ये US ऐसा क्या रहेगा जिसकी वजह से this whole thing would blow up. So what we are saying is ठीक है, poles हमारे ये है. अगर एक और कोई ऐसा let's say अगर यहाँ पे 1 by s आ गया तो मुझे पोल का कंट्रीब्यूशन मिल जाएगा s is equal to 0 पे. I would have non-repeating pole and then it would happen. या फिर I get 1 upon s plus 3 एक और बार. Then also I'll have repeating poles and it would be no, it would not be a problem because it is not on the imaginary axis. So only one case is there. अगर s is equal to 0 एक और बार आ गया then it is a problem because I don't want to have repeating poles on the imaginary axis. Multiplicity 1 चाहिए imaginary axis पे. So what would happen? or that is only possible our US is 1 by S. Now US can be 1 by S only for UT is equal to 1. So only this would create the problem. All of these would not create the problems. They would just add pole at plus minus root 3j और प्लस माइनस रूट थ्री का भी एक और पावर हो जाएगा रूट थ्री जे और कॉस टी वुड बी प्लस माइनस जे यहीं पे कंट्रीब्यूशन आएगा एंड ऑल ऑफ दीज आर नॉट अ प्रॉब्लम फॉर दिस सिस्टम बट 1 by s is literally a problem for this system and 1 by s was a bounded input लेकिन इसके लिए बाउंडेड आउटपुट आ गया ठीक है cos 3t भी बाउंडेड इनपुट था sin root 3t was also a bounded input cos t was also a bounded input all of these three are bounded inputs और इसके लिए we got bounded output but since for at least one bounded input which is unit function what we unit step what we got is the output is unbounded अभी एक बाउंडेड इनपुट के लिए भी अगर आउटपुट अनबाउंडेड आ चुका है तो दैट इज अ प्रॉब्लम एंड द सिस्टम इज नॉट BIBO स्टेबल दैट इज व्हाई वी सेड फॉर एनी अनबाउंडेड for any bounded input because we want to test for all bounded inputs and that can be clearly found out if you know the poles of the system and this would help you everywhere हर जगह पे बैठ के उसका टाइम रिस्पॉन्स टाइम एनालिसिस करने की जरूरत नहीं है see the poles think what would happen if I give this input कहाँ पे और poles lie करने देंगे and how it would affect my stability that would help you okay having done this okay try this question yes Nisha do you want to ask something hello Nisha okay okay so please solve this question first of all find out what is ys upon us this is very
Madam,
first thing you
option
have to
C, madam.
first tell me ys upon
Option
us
C.
now
1 by s is power 4, 1 by s power 4 plus 4s square plus 4.
okay is everyone getting this answer or do you need explanation for this it is just reference from the Laplace table for fourth order differential equation you are going to have s power 4 term coming out for second order you are going to have s square coming out so that is the thing only that you are doing okay since you have got this answer you can just see that it is s square plus 2 का whole square ठीक है now who can tell me what are the poles of the system Surya you please wait for someone else to give the answer I want the poles of the first of all can someone tell me how many poles do we have for the system number of poles
4.
4 right because it is a fourth order equation if it is fourth order we are going to have 4 poles definitely it could be repeated it could be non-repeating anything is possible so yeah what are the poles of the system
S1 minus root 2j.
plus minus root 2j I'll write it once more because there are 4 poles so we have 2 poles as plus 2j so I'll write this like this plus root 2j minus root 2j minus root 2j now if you know this see these two poles are same these two poles are same where are they placed in the s plane first I have to see this where are they placed if it is creating problem then I'll check some other thing so where is their placement one is at root 2j second pole is also here I'm drawing it just beside that but it is at the same point root 2j two poles are there two poles are here minus root 2j Now, do you see that this is the imaginary axis, this is the real axis, and at root 2j itself, there are two poles. Minus root 2j, there are two poles. So, when we were reading this, when we're trying to understand this, so it said if there are repeating poles of the plant transfer function on the imaginary axis, if there are repeating poles with all remaining poles in the left half of the S plane, the system is not BIBO stable. Means for here already the system is unstable. The system is not going to, since the system has pole in such a way. Let that go. Just a second. Yeah, the system already had poles that are repeating on the imaginary axis. System is already going to exhibit unbounded response behavior irrespective of any input you apply. Let's say you choose this input ut is equal to 1, then what you will have? You will just have ys is equal to 1 upon ss into s square plus 2 का square. What would happen? ये तो contribute करेगा ही unbounded होने में. Even whatever this does, s is equal to 0, this is always going to contribute to unboundedness of your आउटपुट. ठीक है, अगर इसको भी चूज किया देन ऑल्सो यहाँ वाला टर्म चेंज हो जाएगा, दिस वुड रिमेन द सेम. If this is chosen, then also this would remain the same. So these poles are already a problem of the system, and this is anyway going to take you to unbounded response of the system. So you give input bounded input, it is not going to work for any sort of input. Any bounded input you give, it is going to explode to infinity because the system is already having repeating poles on the imaginary axis, which is going to take the system output to be unbounded. So for any bounded input, you are going to have unbounded output. So this is important. So see, you got the answer just by looking at the poles, and you had not to do inverse Laplace and going into time domain and taking out the answer. That was not required. You just had to see the position of the poles and you could answer that yeah, this would be the output of the system. You did not have to check what is the input provided to the system and take the inverse Laplace transform. So this BIBO stability is a very important concept that helps you realize if the system is going to be response is going to be bounded or unbounded. It is going to be finite or infinite. Okay. Okay. So here also I want the answer here. Try this question. First, someone tell me ys upon us. Then someone tell me where are the poles of the system. Then we'll discuss.
1 by s square plus 2s minus 3, ma'am.
Okay, that's correct. Good. So where are the poles of the system? Where are the poles of the system?
Ma'am, 1 or minus
1 minute. Just a second, someone is trying to join. Yeah, where are the poles?
ma'am 1 or minus 3. 1 and minus 3.
Right. So, what should be the answer to this question? see the position of the pole. One pole is at, this is imaginary, this is real. One pole is at -3. One pole is at 1. Do you see? You have a pole already in the right half of the S plane. So what was the thing that was stated here? That if there exists even one pole of the plane transfer function in the right half of the S plane, मतलब right half में तो जानवी पाप है. अगर तुमको right half में मिला एक भी pole of the transfer function that has a positive real part, system is not BIBO stable. It is unstable. Okay. So see. Yeah. You already have a pole in the right half of the S plane. System is already unstable. अभी ys is equal to 1 upon s minus 1, s plus 3. You give it 1 upon s. us तुमने 1 दे दिया, ठीक है? यूनिट स्टेप दिया है तुमने. 1 upon s you gave. You see what would happen? It is already exhibiting this behavior. S is equal to plus 1 wala behavior, which makes the system unstable. So you give either this input or this input or this input. फर्क नहीं पड़ता है. All of them cannot do anything because the system already has unstable trait. S is equal to plus 1. Hence, this thing is always going to lead you to unbounded system response for any bounded input. So, the correct option is this one. Okay. So, where did it go? Yeah. So, this is the transfer function. No, not transfer function, differential equation. Which of the following is? So, what is multiplicity? Let's say I say that I have a transfer function where I say I have s square. I just have my transfer function is ys upon us is 1 upon s square. This is only that, okay? What is the pole of the system? 1 upon s square. And how many poles are there? Please answer. How many poles are there? And what are they? Hello, Priyanka?
Ma'am, 0 and 0.
Yes, 0 and 0. So definitely it is of second order, then it is going to have two poles and both of them are 0 only. So if it is 0, that means multiplicity of 0, a pole 0 is 2 because it is appearing 2 times. So the number of time it appears is basically multiplicity of a pole or a 0. Okay. So now you all have known how to find the transfer function very well. I'm really happy that it is very clear to all of you. So can you find out the transfer function of this ys upon us and then try to find out the poles of the system. So that would be difficult because it is going to be a fourth order Laplacian transfer function. But still I want to know the transfer function and maybe later you can find out what are the poles of the system. That's not a problem. But let me know the transfer function. Has anyone got the transfer function? Can someone share what is the transfer function? Else I'll solve.
1 by s power 4 plus 8s cube plus 22s square
Just a
plus
second.
24s plus 9
Please repeat. 1 upon s power 4.
plus 8s power 3
Okay.
plus 22s square
So
plus
22s.
20
Uh,
plus 24s plus
okay.
9.
Very good. So this is the transfer function. You equate this characteristic equation to 0. Find out what are the poles. You will have 4 poles since it is of 4 order. So you'll have 4 poles. Uh,
Minus
I'll
1
tell.
and minus 3.
Please say.
Minus 1 and minus 3.
Very
2
good.
times.
Very good. Very good. So it is minus 1, comma minus 1, minus 3, comma minus 3. So multiplicity of or multiplicity of minus 1 pole is 2, of minus 3 is also 2. Hence, this is the answer. Okay. So this was the last question that we did. Um, yeah. So does any one of you have any doubt in any question, or do you wish to share something? I hope the lectures are well clear. Please go through them before you attempt your assignments and, of course, come for the interaction session. This Laplace transform is always going to form a basic of your whole control system course, so it would always be helpful for you. In the next tutorials, you'll probably see what are poles and zeros, and then you'll have some first order, second order systems that you'll go on seeing uh, in the course. Then you will also know some performance characteristics and everything. So yeah, okay. So we can end this session. If someone has to say something, let me know. Okay, I think everything is done. See you on next Monday. We'll meet at the same time and we'll cover the next week lectures. Okay.